this video, we're going to look at a few different line integrals and talk about how to think about all the different things we've learned about line integrals and sort through all that and decide the best way to evaluate them. So in this video, we're going to focus on work and flux integrals, and then I have another video where we'll look at some other kinds. All right, so I have here a problem. It says for each of the following vector fields and curves, determine how to evaluate the line integral over the curve C of f dot dr. So that doesn't say the word work in it, but you should recognize that this is a form of the work integral. And so when you think about evaluating work integrals, we've learned quite a few things in this chapter about that. So at the beginning, we talked about the work integral and its definition and some different forms for evaluating that. And so when we first did this, this is the form I prefer, but you also might see that written as m dx plus n dy plus p dz if you were in 3 dimensions, or just the first two terms if you're in 2 dimensions. The definition is the line integral over the curve C of f dot t ds. So you might see it written like that also. It's also sometimes called circulation or flow integral. So you should recognize that that's what we're being asked about here. And when we first learned about work integrals, how we did that was we just parameterized the curve, and then we did everything in terms of t and just evaluated the f dot dr or m dx plus n dy plus p dz form. So that's certainly one way that you can evaluate work integrals. But since then, we've learned a couple of other important theorems that are sometimes useful in evaluating work integrals. So the first theorem we learned about work integrals was fundamental theorem of line integrals. And so if fundamental theorem of line integrals applies, then it means that you have a path-independent work integral. So you could evaluate the work integral over an easier path, or even better, find that potential function and just subtract the value of that potential function between the two endpoints. So if fundamental theorem of line integrals applies, then that would be a good way to go. Certainly if fundamental theorem of line integrals applies and you have a closed curve, then that's even better, because your answer is just going to be 0 without having to write down hardly anything. All right, so fundamental theorem of line integrals. The third theorem that we learned that applied to work integrals was Green's theorem. And if Green's theorem applies, it says that the counterclockwise circulation around the curve is equal to the double integral over the region R of the k component of curl. Okay, so what you want to decide is basically, do any of these theorems apply to this problem, or will I just evaluate it the way we started with? So when I think about trying to decide how to do these, one of the first things I check is that curl vector. If you're going to use Green's theorem, you're going to need to calculate the curl vector anyway. And the curl vector is also important for fundamental theorem of line integrals, because that's how you can tell if fundamental theorem of line integrals applies or not. You're going to check to see if the curl vector is 0. If the curl vector is 0, then you have a path-independent line integral. You can find a potential function and use fundamental theorem of line integrals. So for all of these, my vector field and my curve are all in 2 dimensions. So the curl vector is going to be 0, 0, something, and I'll really just need to calculate that k component. So for this first one, my curl vector will be 0, 0, and then the derivative with respect to x of 1 is 0, minus the derivative with respect to y of 2xy is 2x. So that is not the 0 vector, so fundamental theorem of line integrals does not apply. Also, in order to use Green's theorem, remember that you need a closed curve, which I don't have on problem number 1. So neither of those 2 theorems applies. So the best way to do this problem would be to just parameterize the curve and evaluate the line integral. So when you set up that integral, you'll substitute your x and y equations into your vector field equation. You'll calculate your dr based on the parameterization of your curve using r of t equals x comma y as your parameterization of your curve, do the dot product, and evaluate the line integral. Okay, on this next one here, we want to think about whether Green's theorem or fundamental theorem of line integrals is going to apply on that one. And so let's calculate that curl vector. So I'll get 0, 0, comma, and then the derivative with respect to x of x squared plus 2 will be 2x, minus the derivative with respect to y of 2xy will also be 2x. So I do get the 0 vector there. So that tells me that I have a conservative vector field, and fundamental theorem of line integrals does apply. I can find a potential function pretty easily by just integrating each of my components for my vector field with respect to x and y. Remember, the idea of a potential function is that my vector field f is a gradient field. So that first component would have been a derivative with respect to x, so I need to do an antiderivative with respect to x. And then for my second component, I need to do an antiderivative with respect to y. So I'll get x squared y again, and then plus another term, 2y. And then I'm just going to evaluate that at my two endpoints. So my initial point in my curve, my A point is 2, 0, and my B point is 0, 2. And that calculation is pretty straightforward. You get 4 minus 2, so you get 2. Okay, for number 3, this is the kind of problem where you say, yes, and you just write down the answer. Because you calculate the curl vector. We did that in problem 2. We got 0. And we notice that we have a closed curve. The other important thing to note here is that my vector field is all polynomial functions. So that vector field, actually on all of these vector fields and all of their partial derivatives of all orders, I really need first partial derivatives, are continuous everywhere. So our theorems apply here. Our curve is closed. Our vector field is conservative. So those two things together tell us that work is 0. You can get that result either via fundamental theorem of line integrals or Green's theorem. If you use fundamental theorem of line integrals, your A and B points would be the same point. So say you start here at 2, 0. You don't even need to find your potential function. You know that those are going to subtract from each other to give 0. If you use Green's theorem, notice that your curl vector is 0. So if you use Green's theorem, you get the 0 vector here. When you dot that with k, you still have 0. And so you're adding up 0 over the whole region inside the curve, so you get 0. So number 3 is the kind of problem where you say thank you and you go on to the next problem. All right, number 4, I have a different vector field here, so we'll start by calculating that curl vector on number 4. So this is not the 0 vector, so fundamental theorem of line integrals does not apply. I do, however, have a closed curve. My curve is simple, closed, and piecewise smooth. Closed is the thing you usually need to check in order to use Green's theorem. So I do have a simple closed piecewise smooth curve. I have a vector field f that's continuous and all of its first partial derivatives are continuous everywhere. So on this one I can use Green's theorem, and so I'm going to evaluate the double integral over the region R of my curl vector dot k. So the k component of curl, I'll just get this function. And so maybe you go ahead and set up that double integral over the region R. You probably would use polar coordinates if you do that. You'd let R go from 0 to 2 and theta go 0 to 2 pi and convert to polar coordinates. Or maybe you can think about this and just get the answer. I'm going to break this up into some pieces here. And this first term here, this is the sum of all the y coordinates over that region R enclosed by the curve. So if I think about choosing all those points all over there, every place where I have a positive y coordinate, there would also be a negative y coordinate that would balance that out. So this first integral will evaluate to 0. This second integral is 2 times the area of the region R, so I can write that down pretty easily. And the third integral is minus 2 times this integral of x over the region R. And for the same reason that the first integral is 0, the second one will be 0. Every place I have a point inside here where I've got a positive x coordinate, there will be a partner point that has a negative x coordinate. Those will exactly balance each other out when I add up all those function outputs over the region. And so this last one will be 0 as well. All right, so I end up with actually just 2 times the area of my region. My region is a circle of radius 2, so it's easy to write down the answer for this. So I really encourage you to use those shortcuts for finding values of double integrals. That's part of the reason we spent so long on those when we did them. All right, so these were all work integrals. I want to look really quickly at the same 4 problems, but with flux integrals. So I've got the same 4 problems here, and instead of doing a work integral, I've crossed that out, and we're going to do the flux integral. So it might say the word flux in the problem, or maybe you would be given some form of the flux integral, and you should recognize that that's a flux integral. All right, so for work integrals, we had really three different ways to do that. We could parameterize the curve, we could use fundamental theorem of line integrals, or we could use Green's theorem. Fundamental theorem of line integrals is really about work integrals. So unless you do some sort of manipulation to symbolically change a flux integral into a work integral, if you're really going to treat it as a flux integral, you really just have two different ways to do that. The way that we started with, which would be to parameterize the curve and then evaluate the flux integral. So we did flux integrals just in two dimensions. So we had plus or minus the integral over c of m dy minus n dx. So one way that you could evaluate the flux integral is the way we started. And then the only other way we really have to evaluate flux integrals is to think about using Green's theorem. And so that would be the flux divergence form of Green's theorem. And so if Green's theorem applies, then we can apply that. So the big deal thing that we're looking here to determine whether Green's theorem would apply or not is whether the curve is closed or not. So for these first two problems here, the curve is not closed. So for those first two problems, you're going to evaluate just the integral plus or minus the integral over c of m dy minus n dx. And you've got the same curve for both of those, so you're going to use that same basic parameterization. And then when you do that integral, you need to think about the plus or minus. So you think about the orientation of the curve. So your unit tangent vector would be in the direction of the orientation of the curve. And if you do your right-hand rule to think about which way n would be pointing, n here would be pointing away from the origin. We would choose plus for t cross k. So that's how we would do those first two. The second two, I do have a closed curve, so I can use Green's theorem. So for this first one here, when I go ahead and evaluate that right-hand side of Green's theorem, I'll be doing the double integral over the region R of the divergence. So for the divergence, that's del dot f. So I'll apply del x to the first component. I'll get 2y plus del y to the second component. 0. And so again, I'm going to integrate over the region R enclosed by the curve. This is one that, again, you might be able to recognize that this answer is going to be 0. I am going to have 2 times the sum of all the y coordinates at every point inside here, and I've got positive and negative y coordinates that will exactly balance each other out. So this one will end up being 0. For the second one here, when I calculate that divergence, del x of the first component plus del y of the second component. We could do that double integral. If you need to evaluate the integral, you could convert to polar coordinates. You would let theta go from 0 to 2 pi, and r would go from 0 to 2. But this, again, is one that if you kind of have been thinking about integrals and what they mean, you can recognize that when you split this, this one will also be 0. I do encourage you to look for those shortcuts. They don't show up in every problem, but they sure are nice when they do show up. All right, try some homework.